Welcome to the Explainer. When we think of math, we think of something rock solid, right? The ultimate source of truth. But what if I told you there was a kind of civil war raging at the very heart of mathematics? Yeah, really. Today we're diving into this revolutionary idea that says mathematical truth isn't something you just find, it's something you have to build.
So, let's kick things off with a pretty fundamental question. Is mathematical truth absolute? Is it this single, unchanging thing that we just discover? Kind of like finding a new continent on a map? I mean, for centuries, that was pretty much the accepted view. But what if there's another way to look at it? What if truth isn't about discovery, but about construction? All right, so here's our game plan for today. We're going to start with the crisis that kicked this whole thing off. Then we'll look at the two big opposing ideas that came out of it. We'll dig into the core of this constructive revolution, see how it has this amazing link to computer science, and finally wrap up with why any of this stuff is so important right now. Okay, first up, a crisis of certainty. We're talking about a time when the bedrock of math, something everyone thought was completely unshakable, suddenly started to show some serious cracks. Yeah, these paradoxes were one thing, but then Kurt Gödel dropped a bombshell. His incompleteness theorems were a total earthquake. In 1931, he proved something that just blew everyone's minds. Basically, any math system that's strong enough to do simple arithmetic will always have statements that are true, but that you can never, ever prove within that system. Just think about that for a second. Suddenly, that whole idea of absolute certainty was just gone. The dream of finding one perfect system for all of mathematics, poof. It was over.
So, out of this chaos, this rubble, two totally different schools of thought popped up, two competing philosophies about what truth in math even means.
Okay, so this is the heart of the debate. On one side, you've got classical mathematics. These guys believe that truth is just out there. It's an abstract reality. Any statement is either true or false, and that's that. Our job is just to figure out which one it is. But then you have the other side, constructive mathematics. And they say, whoa, not so fast. For them, a statement's truth has to be demonstrated. If you claim some mathematical object exists, you can't just say, oh, it must be out there somewhere. No way. You have to provide a concrete, step-by-step recipe to build it. It really is the ultimate show, don't tell. And that's the crucial point. For a constructivist, a proof isn't just some clever, abstract argument on a piece of paper. Nope. A proof is the recipe. It's the blueprint. It's the literal set of instructions for constructing the thing you're talking about. If you don't have that recipe, you don't have a proof. End of story.
Now this is where things get really wild. To make their whole system work, the Constructivists had to throw out a fundamental law of logic, one that, honestly, seems like total common sense. It's called the law of the excluded middle, and it's super simple, really. All it says is that for any statement, it's either true or its opposite is true. There's no gray area, no middle ground. The light switch is either on or it's off. A coin toss is either heads or it's tails. This idea is basically the foundation of classical logic, and it's how most of us think about the world, right? But then you had pioneers like this guy, L.E.J. Brouwer. He founded a whole school of thought called intuitionism, which is a big part of constructivism. And he basically looked at this law and said, hang on a second. He argued that sure, it works for simple, finite things, but when you get into the wild, infinite world of mathematics, you can't just assume it holds up. So for a constructivist, saying P or not P is only valid if you can actually show how to decide between the two. You need one of two things, either a direct, step-by-step proof of P, or a proof that assuming P is true blows everything up and leads to a crazy contradiction. If you don't have one of those two things, well, then the statement is just undecided. It's in this kind of limbo. It's not proven true. It's not proven false. That middle ground is suddenly back on the table. Okay, I know what you might be thinking. This all sounds like a really abstract, philosophical debate, right? But here's the amazing part. This whole insistence on building things, on having a recipe, it turns out to have a mind-blowing connection to computer science. Just think about it for a second. A constructive proof is a step-by-step recipe, a detailed set of instructions. What does that sound like to you? It's an algorithm. And what do we do with algorithms? We turn them into computer programs. This is the big reveal. A constructive proof isn't just an argument about something. It is a computation. It's a program you can actually run. It's executable code.
And this incredible connection has led to some really powerful tools. I'm talking about things called proof assistants, software like Coke and Nuprol. Imagine a program that can look at another program, check its mathematical proof, and tell you with 100% certainty if it's correct. That's what these things do. This idea is now absolutely crucial in fields like type theory and computability logic, helping us build super reliable and secure software for things you really don't want to fail, like banking systems or airplanes.
All right, let's bring it all home. Why does any of this matter now, today, in our world?
Well, think about it. Our entire world runs on software. I mean, everything. The money in your bank, the plane you fly in, the medical equipment in hospitals. We are betting our lives on the idea that this code is correct. And that's where constructivism becomes a game changer. It gives us this incredible guarantee. If you can write a constructive proof that your software does what it's supposed to do, that proof isn't just an argument about the program. The proof is the program. It's a concrete computation you can trust. And make no mistake, this is not just some dusty old historical debate. It's a super active area of research. I mean, just look at our sources. We found over 50 papers on this topic just from the 21st century. That tells you something. This is a living, breathing field that is right now shaping the future of computing and how we build software we can actually rely on.
So this whole constructive revolution, this alternate path to truth that was born from a crisis, it ended up giving us something incredibly powerful, a way to build our modern digital world that's more robust and more verifiable than ever before. And that leaves us with one last question to chew on. What else do we believe is certain? What other fundamental truths are we just taking for granted that might be waiting for their own constructive revolution? Waiting for someone to come along and ask that simple, powerful question. Yeah, but can you build it?